Assume our vector space V is finite dimensional. Then we say a basis of vector space V is a list of vectors v1 to vn such that these vectors span the vector space V and they are linearly independent. We saw earlier that if a set of vectors spans the vector space and are linearly independent, then the set has to be maximally linearly independent and has to be a minimal spanning set. Thus, if v1 to vn is a basis of V, then the set v1 to vn is maximally linearly independent and is a minimal spanning set. Now you might wonder why we did not define a basis as a set but a tuple or a list. This is because later when we study linear maps, the order in which we consider the elements of the basis would become important. So please bear with me for the time being. But this theorem already tells us some reasons why a basis would be interesting or important. We saw that there is a natural reason to be interested in maximally linearly independent set or a minimal spanning set. And a basis is both these. And hence a basis will be important. Let us now look at two examples. Namely, the only two examples of finite dimensional vector spaces that we know. The first example is Rn. In Rn, we already know one set of vectors that span Rn, namely E1, E2, etc. up to En. Now we will show that these vectors are also linearly independent. How do we show they are linearly independent? To show this, let A1 to An be some constants such that A1 E1 plus A2 E2 plus etc. up to An En is equal to 0. But notice that A1 E1 plus A2 E2 plus etc. up to An En is just the tuple A1, A2, etc. up to An. And by 0, we are actually talking about the 0 vector in Rn, which is the tuple 0, 0, etc. up to 0. In other words, this means that A1, A2, etc. up to An is the tuple that only contains 0 in it. And thus, we have shown that the vectors E1 to En are linearly independent. As these vectors span Rn and are linearly independent, they form a basis. More precisely, the tuple or the list E1, E2, etc. up to En forms a basis. Notice that the tuple or list E2, E1, E3, etc. up to En is a different basis. That means the order matters when we are writing a basis. Similarly, if V is the set of all polynomials of degree less than or equal to n, then we will show that the list or tuple 1x, x square, etc. up to x power n forms a basis. We already saw that these vectors or these polynomials span the set of polynomials. Thus, all we have to do is to show that these are linearly independent. Once again, to show this, let A1, A2, etc. up to An be constants such that A1 into 1 plus A2 into x plus etc. up to An into x power n is equal to 0. In other words, it's the 0 polynomial. We know that if this is the case, then A1 is equal to 0, A2 is equal to 0, etc. up to An is equal to 0 from our knowledge about polynomials, which implies that 1x etc. up to x power n are linearly independent. And thus the tuple 1x, x square etc. up to x power n forms the basis of the set of polynomials of degree less than or equal to n. We will end this video with another result that illustrates the importance of basis. A list v1 to vn is a basis if and only if every vector in the vector space V can be written uniquely in the form V is equal to a1 v1 plus a2 v2 plus etc. up to an vn. As always, there are two sides to prove. So first we assume that v1, v2 etc. up to vn is a basis, and then we show that every vector v can be represented uniquely as a1 v1 plus a2 v2 plus etc. up to an vn. If the list forms a basis, then clearly the span of v1, v2 etc. up to vn is the entire vector space V. In other words, if you take any vector v in V, there exists a1 to an such that v is equal to a1 v1 plus etc. up to an vn. The only question is this representation unique? To this end, let b1, b2 etc. up to bn be such that v is also equal to b1 v1 plus etc. up to bn vn. If you subtract the two equations, you get 0 is equal to b1 minus a1 into v1 plus etc. up to bn minus an into vn. Now, as v1 to vn are linearly independent, this would imply that all bi minus ai is equal to 0, which implies that bi is equal to ai. And this proves that the representation of V is unique. So we have shown one side of the theorem. We have shown that if the list v1 to vn is a basis, then every vector can be written uniquely. Now let us see the other direction. That is, we will assume that every vector v in the vector space V can be written uniquely as v is equal to a1 v1 plus a2 v2 plus etc. up to an vn. This clearly implies that v belongs to the span of the vectors v1 to vn. And in other words, as v was an arbitrary vector, this implies that span of the vectors v1 to vn is the entire vector space. Therefore, all we have to show is that the vectors v1 to vn are linearly independent. To show they are linearly independent, let us assume that a1 to an are constants such that a1 v1 plus a2 v2 plus etc. up to an vn is equal to 0. Now notice that we have another representation of the 0 vector, namely the representation 0 v1 plus 0 v2 plus etc. up to 0 vn is equal to 0. This is a representation of 0 vector that we know. But as we have assumed that there is only a unique representation for every vector, we know that this would imply that ai is equal to 0 for all I, which implies that the vectors v1 to vn are linearly independent. Thus, the set of vectors v1 to vn span the vector space and they are also linearly independent, which means they form a basis. And this completes the proof of the theorem.